Hey, welcome back to Fat Mama Physics. In this video, we are going to continue on with 2.2, which is powers of 10. So, powers of 10 is 0. Last video, you learned that anything raised to the power 0 is going to give you 1. And 10 powers of 10, essentially, you learned that whatever exponent is in the base 10 tells you how many zeros there are in that particular number. So you kind of get a sense of what the powers of 10 look like. We're going to apply that into something called scientific notation. This is something very important with, especially if you're going into sciences, if you plan to take any science course, and also if you get something weird on your calculator, which can happen anytime, then hopefully this lesson will explain some of that for you. So what I mean is the following. When you see something weird in your calculator, I just try to do that with this one that I have here on my computer. You may see something similar or maybe not. But if you take a look, I have this huge trailing numbers. It took me a while to get this. And then you have an E, and then you have a plus, and then you have some number. It doesn't have to be a plus, it could be a minus, and we won't deal with negatives, but if it's a positive, then that becomes really strange, and you don't know what to do with it. Some of you might instead see, something that looks like this. Times 10 to the power of 46, for example. Okay, so some of you might see that. Some of you might see E and then plus 46. These mean exactly the same thing. And yes, you have seen this before, which is times 10 to the power of 46. And you've done that in the previous example where you have seen something with a base 10. 10 to the power 3, 10 to the power 2. This is just 10 to the power 46. And yes, it's the same thing, but it looks scarier. So doesn't matter. It's still the same thing. It's just a bigger number. That's all there is to it. There's more zeros. More money for you. No, I'm just kidding. Okay, so that is what that means. And when you see a huge number, and notice that in your calculator, it has 1 point dot dot blah 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 whatever comes after that decimal. So it's always that whenever you see this form on your calculator, E plus 46 or times 10 to the power of whatever, then this decimal is, it's always there. It's always right after that first number. And that is the signature form of a scientific notation. That decimal place must be after that first non-zero number. So that's very important. So let's take a look at an example. So I wrote an example here, which is a number that is in scientific notation. So a couple of interesting parts of the anatomy of this, is notice that decimal appears after that first non-zero number, and it has to be that case. So whenever you're converting a number to scientific notation, you must put that decimal exactly right after the largest place value that is non-zero. Another signature part of this is the times 10 to the power of, doesn't matter, something. Can be a negative number, but you don't learn that this year, so that's just that. Okay, so that is what that looks like. So how do we convert this to a standard form, something that is in regular notation, in which we call it? So to convert this into regular notation, first of all, we need to appreciate the fact that taking a look at the scientific notation, compare that with what you've seen before in the previous lesson, where you have to write everything out. It was very annoying. And even if it's just to write, say, 50 million thousand, if I wrote 50 million thousand, or if I wrote a huge number in scientific notation, it takes me 1 second to do it. It takes a normal person maybe about 10 seconds to write all those zeros. So it's a very, very efficient way of communicating a number. And sometimes for scientists, since we deal with either with very large numbers or very small numbers, it almost makes no difference whether this is a 9 or a 7, or this is a 6, or this is a 3, or versus a 2, versus whatever it is. Usually we care about this power that deals with something we call magnitudes. So if you think about a good example of that would be earthquakes. So earthquakes, usually we talk about magnitude 1, 2, 3, 4, 5, and of course the larger the magnitude, the bigger the effects of the earthquake. And that's the idea of going up by a factor of 10. And it scales up quite quickly. It's like going up a place value, essentially, is what it means. So for scientists, we deal with magnitudes versus just plain old little numbers. It's not like we're trying to be stingy with our numbers. We just care about the big picture sometimes because we care more about modeling and etc. But of course, sometimes the small numbers do matter quite a bit, especially when we're dealing with very specific numbers like current, electricity and whatnot. Otherwise, we'll blow up a fuse. That becomes important. So, but yes, if we deal with very large numbers, then that's very effective for us to communicate such a number without needing to write the whole number down. Okay? So, how do we convert this to a regular notation, given that we only have one power here? So, if you think of it as a multiplication sentence, then it's essentially 9.0230945 times 10 with 11 zeros. So if we know that this is 10 with 11 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, then we know that anytime we multiply by a 10 or 100 or 1,000, the number of zeros dictate the number of place values we move our decimal by. So if we use that same line of thinking, then I need to move this decimal 11 spaces. Now, which way should I move it? Well, think about this. If I move my decimal place to the left, this whole number is going to get smaller. I'm going to get 0.92 something. And if I move it again, it'd be 0.09. And that doesn't make sense because if I'm multiplying by a 10 to the power of 11, I'm multiplying by a very large number. So this number here, the 9.02 is only going to get bigger. To get bigger, I need to move this decimal place to the right. So if I count 11 spaces, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's ultimately where my decimal is going to end up. Every little bump that I have on the bottom, I'm going to put in a 0. So that's 1, 2, 3, 4 zeros, which means my final answer is going to be 9, 0. Don't forget the zeros that are in between. 2, 3, 0, 9, 4, 5, and 4 zeros. 1, 2, 3, 4. So that's my fully expanded out number after I multiply it with my power. Okay, so that is scientific notation. So what we will do is maybe I will do, say, I'm gonna do the first example, write that as a scientific notation. So I'll do A, you'll do B, and then we'll come back, and then we'll do kind of back and forth. So let's start with 5A. Write the following numbers in scientific notation. So how do I do that? First of all, I know that I have to imagine I have a decimal right there at the very end. So even if the number doesn't say that, there's always an imaginary decimal there. If I want to write it as a scientific notation, then I need to move this decimal so that it is right there, right after that first non-zero number. So ultimately, I need to get that decimal right there, in front of that first 5. So if I count the decimal places I move, 1, 2, 3, 4, 5, 6, 7, 8, 9, I moved it 9 spaces. Okay, so 9 spaces, I'll just write there just to help me out. And then when I write my scientific notation, I always have to write the proper form of it. So that just becomes 5.5. And I don't need to write in all those zeros, so I just write 5.5 times 10 to the power of. And that power is how many spaces I counted, 9, because the 9 means the number of zeros in this power, and that the number of zeros dictate the number of times that I move my decimal. Okay, so that is my final form for A. Okay, so why don't you try B? Good time to pause the video. So for B, again, imaginary decimal right there, moving it twice, 1, 2, to get to right between the 7 and the 8, and 7 being our first number, right after the 0, I get 7.8, and then times 10 to the power, since that was 2 spaces, 10 to the power of 0. Okay, that's our final answer. Okay, so let's do some other examples below. Example 6, we're going to write some of these numbers in regular notation. So I'm going to do A, and you'll do the rest. So A, now the decimal is laid out for us. So we want to move the decimal so that to expand the number out, and this is 10 to the power 4, so I'm going to move that decimal 4 spaces, and since this number is a big number, I will move it to the right, 1, 2, 3, 4. So that's going to give me 1, 2, 3 zeros, and ultimately, which is 9, 6, and 3 zeros. So notice that the 4 number exponent doesn't tell me how many zeros there are in my final expanded number, because depending on how many numbers I have after the decimal place, I have to move my decimal over them, which then takes away me putting there a 0. Okay, so good time to pause for example B and C. Okay, so again, I take this imaginary 0, move it over 6 times. 1, 2, 3, 4, 5, 6. That is 1, 2, 3, 4, 5 zeros. So 7, 1, and 5 zeros. Okay, there you go. And then last but not least, this guy, 3 spaces over 1, 2, 3. 1, 2, 3. Okay, so that's 1 more 0. And there you go. Okay, awesome. Oof, that's a lot of problems. Well then, I'm going to do A, okay, and then I am going to do, I'm going to do E, and then I am going to do, nope, oh, actually I'm going to do H, okay? So I'm going to do these 3 examples, and then we'll come back to do I together, okay? Ooh, so let's begin. Okay, so for A, so notice that these 2 numbers have exactly the same powers. So if we add them, it's like adding 2,300 plus that's 1,000. Okay, so notice that because they share the same place value, I can just add the 1 to the 2 without needing to carry anything over. That gives me 3,300. And if I write this as in scientific notation, which I should, then this is just going to be 3.3 times 10 to the power of 3. And you may have noticed the 3.3 can be exactly me adding 2.3 plus 1.0. So that would be the shortcut for you to do it. And you can probably do it for most of these examples, except when it becomes the case where you have to carry a number over, which is the next example, E, okay? So based off our previous logic, we can just add these 2 numbers here and just have that as times 10 to the power of 3. So if I add these 2 together, 9 plus 2.3, I get 11.3 times 10 to the power of 3. Now, based off of the rules of scientific notation, you can never have the number having with the decimal place in having... Basically, you cannot have 2 non-zero numbers after the decimal. That is not proper scientific notation. So I have to have this decimal right there in order for this to be in a legit scientific form. So it would have to look like 1.13 times 10 to the power of, and since I moved the decimal over, making this number smaller effectively by power of 10, then I need to add 1 to this 10 over here in order to count for that loss on the left-hand side, on the other number. So my final form is going to be 1.1 3 times 10 to the power 4. And if you don't believe me, you can check using your calculator or on the side. Okay, last but not least, remember we talked about carrying over. What happens if we have a number that is much smaller, but we run into a similar case where this number is a little bit funny and it doesn't look like scientific notation? So here I have h. So this is subtracting, and subtracting and adding are going to be quite similar. I'm still going to get times 10 to the power of 3, and since this, after I subtract, is still going to give me a number that is larger than 0, it is in fact 0.3, since 2.3 minus 2 is just 0.3. Now here we have another problem. Notice that this decimal is not in the right place. It is after a 0. We need a non-zero number. So we actually need to move this decimal place over where after the 3. So what that effectively does is I need to multiply, effectively, I need to use one of these guys over here, one of the 10s, to bump that up to a 3 instead of a 0.3. So if we shift this a little bit over, this is gonna turn into a 3 times 10 to the power of, and if I need to borrow a 10 over here, then that's gonna be 10 to the power of 2 instead. Okay, so that is, now that's what I have to do. I can't just leave my answer as the one you see above. You have to write it in proper scientific notation. So I'm gonna give you a chance to do B, C, D, so this guy, C, D, F, and G, using all the skills that we've learned, and we'll come back together to do I together. Okay, good time to pause the video. Okay, and here we go. I'm going to fly through these examples, so watch us go. So 4 plus 3, that's going to give us 7, and then the scientific notation is going to be the same. Here we have 4.5 minus 3, that's still going to be the same power. That gives us 1.5 times 10 to the power 5. Okay, and then over here, 8.0 minus 1.2, this is going to be 6.8. Okay, so that's 6.8 times 10 to the power of 7. And then, this is the case where you have to do a carryover here. So 3.9 plus 8.1, this is going to be, oh, that's pretty nice. That's just 12. Okay, so yes, it will look like 12 times 10 to the power 2, but because we need to put the decimal place in the right location, then that effectively means that I need to add one more exponent over here to make sure that I count for the loss over on this side. So that's 1.2 times 10 to the power of 3 instead. Okay. And then over here, I get a similar case as h, where after I subtract these two, I'm going to get 0.1 times 10 to the power 6. To write this in proper scientific notation, I got to borrow one of these 10s over here to give me 1 times 10 to the power of 5. Whew, all right. Last but not least, I. Okay, so let's do I together. Okay, so we will, in this case, still have, it looks like, 10 to the power of 3, but we are subtracting, and we are going to get this subtract by 4 is definitely going to give us a negative number. So what I'm going to do is I'm going to actually do it where I take the 4, subtract it by 2.3, and then make the whole thing negative. So that's going to give us 1.7, and that's times 10 to the power of 3. And you're wondering, if I'm dealing with negatives, doesn't all of these affect it as well, the times 10 to the power of 3? Well, if you are thinking of it that way, then imagine that I have 2300 minus 4000, and this is going to give you negative 1700, which then in scientific notation looks exactly like that. Okay, so there we go. That was scientific notation. So I congratulate you for making it all the way to the end of this video. I thank you for watching. I wish you the best of luck, and Fat Mama Physics signing out.